Hello, welcome to this lesson in the AC Circuit Analysis Tutor. Here we're going to talk about the concept of the definition of average power. I told you we're going to chop this stuff up into little bite-sized chunks, and this is an important bite-sized chunk. We're going to define average power here, and then we're going to continue to define it and pull information out in the next section here. All right, so the concept of average power is not too hard to understand. If you remember the instantaneous power, we drew it on the last section for the resistive case. You remember it looked like a sinusoid, but it never went negative. It was always on top, positive like that. So sometimes it's going up to a maximum, sometimes it's going down to zero for the resistive case. Sometimes it's going up, sometimes it's going down. But you can kind of see that there's an average there. Somewhere between the hill and the valley, there's an average power associated with that resistive load. And so we need to figure out how to calculate it, but not only for resistors, but we need something that's going to be valid for inductors, capacitors, and mixtures of all three of them. So we need to start at the basic fundamental definitions to arrive at what we're talking about. So we're going to recall the instantaneous power. And that was the following. Small p, little p, is equal to Vm times Im, these are the amplitudes, times the cosine of omega t plus theta v minus theta I times cosine of omega t. Now, if you don't remember this, go back to the last section and you'll see exactly where it comes from. Basically, we have the current defined, the voltage defined. We did a shift on both of them to put us in the right frame for our reference. And now we're just multiplying them together. This is instantaneous power. And we did the resistive case where we drew the three plots, and we did the multiplication and kind of looked at what would happen for a resistor. How would we calculate, if you wanted to figure out what the average power was over some period of time, how would you figure out what it is? Well, you can see these are oscillating things. They're going to go up and down no matter what, all the time, always moving. So how do you calculate an average? So the average power, right? The average power we call capital P. This is why I've denoted it. I know they look similar. This is small p, this is capital big P. You define it over one period. Because when you think about it, if you can figure out what the average power is over one period, then that's the answer. Because everything just continues to repeat over and over and over. So when you're talking about average power, you're really talking about what's happening over one period. Then whether or not I look over 1 second or 10 seconds or 20 seconds, the average is always going to be the same once I've locked it down over one period. But since the thing is changing all the time, normally what do you do to average things, right? If I want to average grades, I add up all the grades, like 95 plus 97 plus 92, add them up, divide by 3, because I have 3 grades, right? And I arrive at an average representative value of those 3 grades. But since this is a continuous function, I can't really add them up so easily unless I use an integral. That's the thing that adds up infinite little functions, infinite parts of little functions like that. You end up getting the area under the curve that's basically adding up the values of all of that stuff that the function represents. So if we want to write it down, we're going to use an integral. So we'll say that capital P, which we're calling the average power, is equal to 1 over t. I'll explain why in a second. Then you're going to integrate from some value t naught to some value t naught plus capital T. And you're integrating the instantaneous little p dt, okay? This is the equation that basically calculates average power. So forget about this for a second.